compute spectrum. We've discussed Google Compute Engine at the very left end of the spectrum. I'm now going to skip over Google Kubernetes. We'll discuss that at the very end of the course, and I'll move on to Google App Engine. Google App Engine is the hosted framework for web applications on the GCP. Now, those of you who worked on Azure and AWS, maybe you can write in on chat what is the equivalent of Google App Engine on Azure and on AWS. So hosted web applications on AWS and Azure. You can let me know. Meanwhile, I'll go on and discuss what Google App Engine actually is. So if you're a developer and you want to build a web application and you don't really want to provision resources, you don't really want to configure networking, you don't really want to set up a load balancer, you just want to write code. In that case, you might choose to deploy your application on Google App Engine. BD and RC are absolutely right. Elastic Beanstalk on AWS is the equivalent of App Engine, and AL, you're also right. Azure App Service on Microsoft Azure is the equivalent of App Engine. Excellent answers, all superb. Cool. So Google App Engine is the web framework and platform where you just write code for web applications, and just with a few clicks, you'll just deploy that code. App Service and Beanstalk is write API. Cool. Now, App Engine has support for a limited number of runtimes and services, but this is constantly expanding. So at this point in time, you have Java, Python, Node.js, multiple versions, .NET, Ruby, Go, PHP, etc. Okay. Now, the whole idea of App Engine is you do not have to provision and administer virtual machines. Right? You focus on development and writing code. All of the infrastructure, all of the versioning, all of the scaling is taken care of by the platform. And the platform here is the GCP. Okay? Now, when you're working on App Engine, you have a pick of two environments. You can choose to go with the standard environment or the flexible environment. And they have very different use cases and they have different kind of strengths and weaknesses. When you choose the App Engine standard environment, your application, whatever web application you're deploying, whether it's in Node.js, whether it's in Python, it runs in a proprietary sandbox. So Google has its own proprietary sandbox, which it will use to kind of containerize your application. So it's its own sandbox. I don't think you can even use the word containerize here. So your app will run in a proprietary sandbox. And this proprietary sandbox is very, very fast to bring up your application. So when your application needs to scale, so let's say you're receiving just 10 requests per second and suddenly that grows to 1,000 requests per second, and your application needs to quickly scale and you need to spin up new virtual machine instances, the proprietary sandbox works in such a way that new instances are spun up in a matter of seconds. Okay. But the standard environment has a few limitations. Google only says you can only use these few languages and few versions of these languages to write code. I won't support everything. So they support only a limited set of runtimes. So though that is gradually expanding. So also, if you're running your app within the standard environment, you can't say, oh, I want to access this port in the underlying compute engine, or I want to access this operating system driver. So you can't access compute engine resources. And another major limitation is you cannot install any arbitrary third-party binary. So you can't just say, oh, I want to use this service, this cool Python package, and I want to use that. You can only use those libraries that Google supports for the standard environment. Okay. On the other hand, let's say you want a little more flexibility in deploying your application. You can use the App Engine flexible environment. As the name suggests, it's more flexible because Google does not use its proprietary sandbox for running your applications. It uses Docker containers. So it's essentially containerizing your application using Docker and running them on compute engine virtual machines. Okay. New virtual machines can be started up in minutes. So when you scale, it takes a minute or two for the new VMs to service your requests. But you can code in many more languages and versions, right? Many more runtimes are supported. Custom runtimes are also supported. You can also install and access third-party binaries. So you can just say, oh, this is a package I want to use because, it's amazing for my specific use case. You can install and use that within the App Engine flexible environment. Okay. So why would you choose one over the other? If you have an app, okay, that experiences traffic spikes, right? So you have just 10 requests per second, then suddenly it goes to 10,000, then it goes to 500, then 1,000. It keeps fluctuating, right? Then you use the standard environment, and typically the standard environment is used for stateless HTTP web apps. With flexible environment, you go for more complicated apps, right? You need lots of third-party binaries, more general purpose. You need to install a bunch of things. You need to use your own custom packages. Then you choose the flexible environment. Typically, these apps have more consistent traffic because they don't scale up that quickly. Okay. The App Engine app is basically one application resource, but an application is not monolithic, right? It can contain a number of services. Every service will have its own version, and these services will run on different instances. So you have an application here on top made up of multiple services. Each service is versioned separately, and each service can run on different VMs. Okay. Next, now we'll go to the very right end of the spectrum and we'll talk about serverless functions, that is Google Cloud Functions. I noticed there are a bunch of questions come in. I'll answer that in just a bit. But meanwhile, I have a question for you. Google Cloud Functions. What is the equivalent of Google Cloud Functions on AWS and on Azure? So those of you know the answer, just type that into chat. What are cloud functions? Event-driven serverless compute. The whole idea of cloud functions is you concentrate only on writing code that reacts to external events. And these events can be HTTP events. These can be events because something happened on another product on the cloud platform. Like somebody uploaded a file to a cloud storage bucket. Somebody pushed a message to PubSub, which is the real-time messaging service on GCP. Somebody added a row to a particular database. Any of these can be events. And U1, all of you guys are right. AWS Lambdas, right? U1, AL, HA, Azure Functions, also correct. SM, PK, SR, all of you guys are absolutely spot on. So Google Cloud Functions, the equivalent on AWS is Lambdas. The equivalent on Azure is Azure Functions. Okay. So event-driven serverless compute is what happens. An external event occurs. Somebody goes in, uploads a file to a cloud storage bucket. Somebody deletes a row from a database, adds a row to a database. Somebody pushes a new message to a topic on PubSub. That's an event. Those are all examples of events. Somebody makes an HTTP request to a URL. That's also an event. GCP is if you can basically set up your cloud function to be triggered in response to these events. Okay. When the event occurs, the platform will essentially say, I have this cloud function which is listening on exactly this event. Right? The platform will then bring up your cloud function and trigger the execution of your cloud function. The cloud function code will then run in response to that event. And of course, your cloud function code can then access any other service on the GCP and do whatever it needs to. Cloud functions tend to be very small bits of code, very like isolated small bits of code. Of course, nothing says that a cloud function has to be small. It can be arbitrarily large, but they tend to be very event based. Okay? So types of events, you can have HTTP events, and then you have background events. Background events can be triggered from cloud storage, PubSub, from logging APIs, from Firebase. We'll talk about the Firebase platform in a bit. Okay? All of these can trigger events. There are limited runtimes available. Okay. For cloud functions, you can code in Go, Python, JavaScript. I believe Node.js is also available. Okay. Concurrency and scale. The whole idea is a single instance of a cloud function is stateless. So you should not have your cloud function share memory or variables with other instances of the cloud function. That's not even possible. Okay. Essentially, each time you receive a request, a new instance of the function is created to service that request. So if 1,000 requests come in, 1,000 instances of your cloud function will be created. Okay. Here I mean instance, that is an instance of the cloud function, not a virtual machine instance. So the best practice is cloud functions should be stateless. They can, of course, access persistent storage. They can access BigQuery. They can access Cloud SQL. They can access any database. So cloud functions, these are the simplest options for writing code, right? But they have a very specific use case. They are event driven. Okay. Deployment of cloud functions, very, very simple. It's simply like 1 or 2 clicks for deployment. All of the software and infrastructure on which the cloud function runs, managed by Google. You are not managing any of these. Okay. And it's also cheap because you only pay when the code runs. But just because you deploy a cloud function, if nobody calls the cloud function, you're not going to pay anything. Okay? All right. Let's quickly do some polls and I'll answer the questions that have come. And I'm going to look at the clock here and make sure we do only 30 seconds per poll. So App Engine is what Google itself, Gmail, Maps, etc. actually runs on. Is that right? I actually do not know for sure, but I do know many, many projects on the GCP run on App Engine. And in fact, when the GCP first launched back in 2008, the first service they launched was App Engine, even before they launched virtual machines. Even before they launched virtual machines. I'm just going to look at. For flexible environment, VMs are automatically provisioned to run the app in a container on the VM. Yes, that's correct, PB. That's correct. Uh, do cloud functions have a similar limitations to lambdas? Yes, they have short timeouts, and you can configure the timeout, but they tend to be short. All right, I'm going to look at the responses here. Snapshots are incremental and used to back up data. That's absolutely right. Next poll, again, one function instance per request. That is correct. So when a request comes in, a new instance of the function is spun up to meet that request. So every function instance will service only one request. So I was actually looking for a document. There was one question here for which I wanted to look up the documentation to give you the link. AWS EB provides option to use custom images. GCP does provide this option AP. Here is a link for you to see exactly that. If you look at the flexible environment link, you can see that you can provide your own custom images on flexible environment. All right. I'm going to look at the responses here. Which of the following is true? Runs in a proprietary sandbox is absolutely correct. Okay. Next poll question. Is this speed for poll questions okay? Everyone who's on this training, is this speed kind of okay? I'm going slightly faster. So U1 clearly feels it's okay. Anyone else, please? Yeah, great. Awesome. Thank you. Thank you all for responding. I'll kind of stick to the speed. So standard environment and flexible environments both have different sets of runtimes they support. So here is the list of runtimes for the standard environment. All right, I'll wait 5 more seconds. And then we'll do one last poll and then we'll move on to storage. So we'll move on from compute to storage. We'll come back to Kubernetes at the very end of this class. All right, I'm going to look at the responses here. Runs within a Docker container? Absolutely correct. So 71% of you got it right. If you can install third-party libraries. Last poll question. This is a very easy one. Only 20 seconds. I'm only going to wait 20 seconds. All right. 5 more seconds. I believe, BB, it does have to be a Docker container. I believe it does, unless they've defined something very recently. So if you look at their documentation for custom runtimes, you see it does have to be, they only talk about Docker containers, unless there's some fine print there that I'm missing. Okay, let me look at the responses. Cloud functions, absolutely correct. Let's move on to storage technologies on the GCP. We've discussed choices in computing. We've already discussed the main compute choices on the GCP. We haven't discussed Kubernetes. We'll come to that. Let's talk about storage technologies. So where is data stored? Now, in order to figure out where you should store data, the first question you should ask yourself is, what kind of data do you have? Is it unstructured data or is it structured data? Unstructured data is essentially data in the form of bytes, right? Binary data. Examples of unstructured data include image data, video data. All of this is unstructured data. On the other hand, structured data is data that has a schema, right? It has at least a partial schema. You kind of know what fields there are, what values the field has, right? There is some structure to the data. We'll talk about unstructured data in a bit. Let's talk about the options you have to store structured data on the GCP. Once you know your data is structured, that is, it has a schema, the next question you ought to be asking yourself is, what kind of transactions or what kind of operations will I be performing on this data? Will I be doing OLTP, that is online transaction processing, or will I be doing OLAP, online analytical processing? Transaction processing is essentially when you perform create, read, update, delete operations and you want ACID properties on your data. You want atomicity, consistency, isolation, and durability. So you want to be basically, you want transaction support, you want transactions all to be executed atomically or none of the transaction statements to be executed. That's OLTP. With OLAP, right, and with OLTP, each operation is fairly short. It's probably finished in a matter of seconds, right? With OLAP, you have long-running jobs to extract insights from your data. So your jobs can run for many minutes, many hours, many days, or weeks. So long-running jobs to extract insights from your data, that is OLAP. Let's say you want transaction processing, then the choices you have on the GCP are you store your data within Cloud SQL. Cloud SQL is just your regular relational database, whether it's SQL Server, PostgreSQL, or MySQL, lifted and shifted to the cloud. So the RDBMSs that we are all familiar with. You can also get OLTP using Cloud Spanner. Cloud Spanner is Google's proprietary technology. This is a horizontally scaling, globally distributed database for transaction processing. Cloud SQL can only manage terabytes of data. Cloud Spanner can store petabytes of data and allow you to run transactions on petabytes of data. Now, for analytical processing to run long-running jobs to extract insights, you can choose to store your data in BigQuery, that is Google's data warehouse. So BigQuery is one of the best products of Google. BigQuery is very similar to Snowflake if you've used that in the external world. Okay. BigQuery and Snowflake are considered to be competitors. BigQuery, of course, came first. It has existed for many years, and it's one of Google's flagship products. There are many organizations, they may not use other GCP technologies, but they do use BigQuery. And then for another technology you have for analytical processing is Bigtable. Bigtable is Google's columnar data store. So if you've used HBase in the real world, Bigtable is HBase plus plus. It's a columnar storage for very low latency, high frequency access. Okay. So these are the choices you have for structured data on the GCP. These are not an exhaustive list of data storage technologies. We'll cover that. Again, not an exhaustive list. We'll cover a few more in a bit. Let's turn our attention to unstructured data. Unstructured data can be stored in block storage or object storage. Okay. Block storage we've already discussed. This is physically addressable storage accessible from compute. So block storage is essentially persistent disks. Block storage is physically addressable storage, meaning you actually laying out blocks of data, like regular size blocks of data in contiguous memory locations and accessing those. Okay. Object storage is logically addressable storage, accessed not only from compute, that is not only from the services, from different services, but can also be accessed by human storage. Object storage is when data is stored in the form of blobs of bytes in some logical format that is understandable to us humans. Okay. Now we've already seen persistent disks before. Let's see how they compare with buckets. Buckets are for object storage. Persistent disks are for block storage. So persistent disks, you can't logically say, oh, I want like this file or such. Usually persistent disks are your hard disk drives. They have like some kind of, you store it in contiguous locations. There is no UI for accessing data on persistent disk. So it's block storage. Persistent disk can only be 64 terabytes in size. You cannot have more than 64 terabytes for one VM. Persistent disks are pay what you allocate. So if you allocate 100 GB persistent disk, you pay for the entire 100 GB, even if you store only 1 GB of data. Okay. Persistent disks are also, they are the hard disks for your virtual machines. You generally do not use persistent disks if you're not creating virtual machines. Okay. And persistent disks are bound to one zone, that is one data center, or to a region, that is more than one data center in the same geographic location. Okay. But buckets are object storage, meaning buckets are just blobs of data stored somewhere. They're infinitely scalable. Once you create a bucket, you can keep adding as much data as you want for a bucket because buckets are pay what you use. If you store 100 GB of data in a bucket, you pay for 100 GB. If you store 1 MB of data in a bucket, you pay for 1 MB. Buckets can be accessed from compute engine virtual machines, but they are not tied to a virtual machine. You don't create a bucket when you create a virtual machine, whereas you create a persistent disk when you create a virtual machine. They're completely independent of virtual machines. Any technology on any service on the GCP can access buckets. And you can access buckets globally. You can access them from anywhere in the world. Now, let's talk about Google Cloud Storage Buckets. And as I'm discussing this, you guys can tell me cloud storage buckets, the same technology is available on AWS as well as Azure. So just type into the chat, what is the equivalent of cloud storage buckets on AWS and on Azure? So when you create a bucket on the GCP, you have to define a storage class for that bucket. And that storage class is based on how often you plan to access the data within that bucket. So the first question you ask yourself is, how often am I going to access this data? Now, you might say, I'm going to access this data very rarely. That's at the left end of the spectrum, or not that often. That's somewhere in the middle of the spectrum, or I'm going to access this data all the time. That's at the right end of the spectrum. Okay. And S3 is absolutely right. SP, U1, PK. Okay. SM is right. Blobs is right. S3 is right. Excellent. Blob storage on Azure, S3 buckets or simple storage service buckets on AWS. That's the equivalent of Google Cloud Storage buckets. So here we are along the spectrum. How often is the data accessed? Data that's accessed very rarely, and you can, we have a loose definition for very rarely. Maybe you access that data less than once a year. That data is referred to as cold data. Okay. If you say that data is accessed only about once a month, you can say, I don't access it that often. That's cool data. Data that's accessed all the time is called hot data, many times a month, many times a day. That's hot data. If you want to store hot data, you choose the standard storage class on the GCP. Standard storage class is for data you access all the time. If this is data that you don't access that often, maybe once a month or once in 2 months, you choose the nearline storage class on the GCP. And for very cold data, like data you're going to access only once a year, once in 2 years, really backup archival data, you choose the cold line storage class. Okay. For all of these storage classes, so far we've learned 3 storage classes: standard for hot data, nearline for cool data, and cold line for cold data. For all these storage classes, the next question you ask yourself is, where is this data going to be accessed from? Where are my users located? Now, if you say that all my users are all in the same region, they're all in South Asia, they're all in the east coast of the US, they're all in Europe, they're all in Australia, you choose a regional bucket. Okay, because all of the data will be stored only within that one region. But let's say you have users spread out across multiple regions, east and west coast of the US, okay? Or multiple locations in Europe. You'll choose a dual regional bucket. Your data will be replicated across multiple regions, that is 2 regions. Finally, if your users are spread out across the world, for lowest latency, fastest access, you should choose a multi-regional bucket. Okay, you should choose a multi-regional bucket. So this will basically store your data in multiple regions, 3 or more regions. Okay. Now, storage classes, why do they matter? Because they affect the cost of storing data. Standard storage has the highest cost per GB per month. Cold line storage will have lower costs per GB per month. Okay. The cost of storing data is highest in standard storage, lowest not in cold line. There's something called archival. I'll discuss that in a bit. Okay. The cost of accessing the data that you've stored is the highest towards the left end of the spectrum, towards cold line storage. There is no cost to access data in standard storage. Absolutely no cost. Okay. And nearline storage is somewhere in between. Okay. Google has one more storage class which they introduced recently, only about a year or 2 ago, called archive storage, and that is even colder than cold line. It's meant for data that you access even less often, maybe once every 2-3 years, only in the case of major disasters. Okay. Archive storage is the lowest cost storage, so lowest cost per GB per month. Okay, but it has the highest data access cost, and there is a 365-day minimum. So once you store data in archive storage, Google, and if you delete it before 365 days, Google will charge you a penalty. Okay, so you have to keep your data at least for 365 days in order to not incur that penalty. So archive is the lowest cost, but the highest cost of accessing data. Lowest cost of storage, highest cost of accessing data. Okay. Now, here I'll talk about Glacier. You mentioned S3 Glacier, right? So Glacier is Amazon's archival service, but the technology on which Glacier is built is different from the technology of S3, as far as I remember. Okay? But Coldline and Archive and all of the storage classes on the GCP are built on the same underlying technology. So it's not slower to access data from Coldline storage or Archive storage because they're built on the same technology. It's just more expensive. Okay. So Coldline and Archive storage has the same speed of access as other storage classes, unlike Glacier and S3. Now, I'll answer one question which has come in because it's relevant to what I'm about to say. Storage classes are not global or regional. They are a different attribute of buckets. In addition to storage classes, you need to specify whether you want your buckets to be regional, dual regional, or multi-regional. They are two different axes. Okay. All right. So different storage classes, they represent different trade-offs, and these are the parameters along which you compare storage classes: availability, storage costs, retrieval costs, durability, access frequency, and use cases. Availability, all of them are highly available, but standard storage, dual regional, and multi-regional have the highest availability. Okay. Storage costs. Standard storage costs 2.6 cents per GB per month. Coldline only costs 0.7 cents per GB per month. Archive actually costs 0.4 cents per GB per month. Okay. Retrieval, notice that standard storage has no retrieval costs. No retrieval costs at all. But nearline and Coldline storage both have retrieval costs, 5 cents per GB for Coldline. So you can see accessing your data, if you've stored petabytes of data for disaster recovery and you need that data, you have to pay. Okay. Durability, retrieval cost, there is no early deletion charge for standard storage. But for nearline, if you delete your data before 30 days, you'll incur a charge. For Coldline, if you delete your data before 90 days, you'll incur a charge. Okay. They're all very durable, so you won't lose your data. Access frequency, use standard storage if you're going to access your data very often, almost daily. Nearline and Coldline, less than once a month. Okay. And use cases, this should be pretty obvious. Standard storage is anything which backs your web app, which is being accessed continuously. Serving websites, static images, right? If you're storing data from a mobile app or a gaming app, everything is standard storage. Okay. Standard storage is regional if you're accessing a data from a compute engine virtual machine, which is in a particular zone. Okay. Nearline and Coldline are both disaster recovery. Archive is also disaster recovery. Okay. File storage versus object storage. File storage, we are used to file storage on our local machine, right? And we know that file storage has a hierarchical structure. You have folders, subfolders, and then you have files. Object storage is actually just flat storage. But in order to help users to logically organize their blobs, the nested structure, the fact that you can create folders and subfolders in object storage, that is just a simulation. So please remember that folders and subfolders within object storage, they are just simulations. Under the hood, your object storage is only storing the blobs. File storage, when you write to a file, you lock the file, nobody else can write to it. There is no locking in object storage. Okay. If multiple people write to the same file, last write wins. File storage has a certain format, right? There are directory headers, file headers, and your file system knows how to navigate that format. Object storage is just an unstructured series of bytes. Let's do a poll, and I'll answer some questions that have come in as we do this poll. It's just a single poll. Storage classes are only applicable for object storage. That's correct. Absolutely correct. Does GCS have auto tiering data movement across multiple tiers based on usage patterns? Excellent question, PK. I don't believe they have auto tiering, but you can set object life cycles. So you can say that after after 30 days. So let's say you're storing log files on cloud storage. You can say after 30 days, move my log files to from standard storage, move it to nearline. And after 50 days, move it to cold line. And after 1 year, move it to archive. So you can set up lifecycle management like that. That's an interesting piece of information about S3 and Glacier, the replication. Thank you for letting me know. But remember, the replication in GCP is based on those regions. They don't tell you what replication factor they have, but where are they? Where is the data replicated? That's based on whether it's regional, dual regional, or multi-regional. So hopefully that answers all of the questions that have come in, and I haven't missed anything. Oh, Bigtable is DynamoDB? No, the equivalent of Bigtable will be like HBase. That the equivalent of DynamoDB is Google Firestore. Google Cloud Firestore is the equivalent of DynamoDB. Bigtable is like HBase. That's a completely different format. All right, I'll wait 5 more seconds and move on. And we'll talk about the other storage technologies. We'll do a quick overview and then we can take a break. All right, I'm going to take a look at the responses. Low cost of storage, high cost of retrieval. Absolutely correct. Excellent answer. Everyone got it right. Awesome. So let's talk about storage use cases. Here I'll quickly give you an overview of the different storage technologies, literally like a one-page overview. We won't go deep. If you're interested in these storage technologies, I recommend that you attend my Google Professional Data Engineer certification. There I cover these different storage technologies in much more detail. So I'll talk about the use case, the GCP service, and the non-GCP equivalent. Block storage, we've already discussed persistent disks and local SSDs in a lot of detail. On other platforms, we have elastic block storage on AWS, Azure Disks on Azure. For object storage, again, we've discussed this, Google Cloud Storage buckets on the GCP, S3 on AWS, blob storage on Azure. If you have relational data, that is, relational data is data, usually tabular data in the form of tables which have relationships with other tables. And for small payloads under 30 terabytes, you will choose to store your data in Cloud SQL. Cloud SQL is just whatever MySQL, PostgreSQL, SQL Server, RDBMS lifted and shifted to the GCP. Okay, so it's a managed service on the GCP, but it's just the SQL that we are familiar with. Okay. On other cloud platforms like RDS or Relational Database Service on AWS is an equivalent of Cloud SQL, or on Azure we have the Azure SQL Database. Yeah. If you have relational data, that is data on which you have you want to perform transactions, right? Transaction support, atomicity, consistency, isolation, and durability, ACID properties, and you have petabytes of data. You cannot use Cloud SQL. Cloud SQL does not scale. The right GCP service is Cloud Spanner, and Cloud Spanner is Google's proprietary database technology. It's a cluster of machines. So you have a cluster of machines providing transaction support, and it can be a globally distributed cluster. So the users can be across the globe. So it's a very, very cool bit of technology, quite expensive. Cloud Spanner is the data model is unique to Google, and equivalent on other cloud platforms is Aurora DB, which I believe is on AWS, if I'm not mistaken. If you have XML documents or JSON documents, and you want to save those JSON entities within a store, the right GCP service is Cloud Firestore. So that is a document database on the GCP. Okay, and the equivalent of Firestore on other cloud platforms is DynamoDB on AWS and Cosmos DB on Azure. Okay. Next, let's go on. Again, no SQL access, but you have naturally ordered data, time series data, IoT devices data, financial data, which is usually time series data, and you want like a columnar store. You have a very large, sparse data set. Bigtable is the right GCP technology for storing this data. There is no equivalent of Bigtable on other cloud platforms, but all of them offer some version of HBase. So the equivalent of Bigtable is HBase on other cloud platforms. And finally, if you want SQL access but to run analytical queries, like analytical queries are basically jobs that run for minutes or hours or even days to extract insights from your data, you use a data warehouse for this. BigQuery is Google's data warehouse. The equivalent of BigQuery on other cloud platforms is Redshift on AWS and Azure SQL Data Warehouse within Azure Synapse Analytics on Azure. Is this table clear? I just want you to kind of look at this table and map the technologies, and I'll do one slide of overview for each of these technologies so that the names and the use cases are clear in your head. I just want you guys to look at this table and make sure that everything is clear, and let me know if it's clear. BB, both Cloud Spanner and Cloud SQL are managed services by Google. So it's not that one is Google managed and another is user managed. Both are Google managed. Obviously, some administration you have to do, a minimal level, but they are both managed services by Google. They are just different use cases. See, Cloud SQL is just the same old technology we have been using since the 90s, but on the cloud. Cloud Spanner is new technology